Tonight's trend is going to be the discussion of the atomic radius, which is the radius of the atom. So the first problem with the atomic radius is how do you start measuring the radius of an atom? So you measure the diameter and take half of that, or how do you do this? So what happens is the problem with the atom is that electrons don't actually go in these perfect little orbits. In fact, they actually exist in this cloud-like state, okay? And we'll talk about this further in a different unit, but they exist in this cloud. So if you were to look at a cloud up in the sky, could you define exactly where one cloud ended and where one cloud started? Or could you exactly tell me just even where one cloud ended on one side and started on the other side? You couldn't. So that's the exact same problem that happens with the atom, is because these electrons actually exist in this cloud-like state, you have to be able to define it differently than a traditional just spherical situation. So what they do is they measure more than one atom at a time, and they choose a diatomic molecule, which is two atoms of the same type of substance. So for example, this would be a hydrogen and this could be a hydrogen. And what they do is they can spot the nuclei or the nucleus. So they've got these lovely nucleuses here. And what they do is they take the distance between these two guys and then they take half of that, and that is determined to be the atomic radius. So the atomic radius is defined as half the distance between two nuclei of a diatomic molecule. So once we've got our definition down of how we can measure it, what is the trend going down a family or a column? What is the trend going across a row, okay, or a period? So what happens is when you go down the family, it's pretty self-explanatory actually if you think about the reasoning why, which we saw on the previous videos about why these trends occur. What do you do when you're going down a family? Well, what you're doing is you're adding energy levels. Okay, so when you add energy levels, what happens to where those outermost electrons are located? Well, they get further and further away, which means what happens to the atomic radius? They become larger and larger. So as you go down a family, as you go down, it increases in size. So atomic radius or size going across a period. So from left to right, we'll always be talking about left to right. What happens? What is the general logic for atomic size? Because what's weird is that even though your mass gets larger as you go across a period, your size actually gets smaller. Okay, so think about that. Even though your mass increases, your size gets smaller. And so your mind goes, pfft, I don't understand any of this now. Well, let's go back to the reasoning back when we talked about the periodic trends. What is happening when you go across a period? Well, what you are doing is you are increasing that nuclear charge. Remember that number of protons. So we've got the +3, the +4, let's just go to +5, okay? That's your nucleus. Overall, you're on the same energy level, so they are relatively similar starting distance. But what happens is as you increase your nuclear charge, these electrons in the outermost energy level are more and more attracted. Well, what are things going to do when they're more attracted to something else? They're going to move in closer. So because your charge gets larger as you go from left to right, these electrons become more and more attracted to the nucleus, so they actually become closer and closer. So your size actually decreases as you go from left to right, your size decreases. So it's really important actually for all of these trends. It's easiest if you just identify the largest one on the entire periodic table and then figure out the trends after that. So we know that from left to right, it decreases as far as atomic size. Why do we know that? We just talked about it. So what that means is that if we go right to left, it's going to increase. So this column is going to be larger than the noble gas column. All right. Now what we're going to do is figure out what happens. Is it going to be hydrogen is the largest or francium is the largest? So what we want to do is we have to figure out what happens as you go down a family. Well, when you go down a family, you're adding those energy levels, so your size increases. So what is the largest one? Hydrogen or francium? Well, that would be francium. So how I remember is that AR, or atomic radius, is FR, or francium. So the largest one for AR is FR. AR, FR, AR, FR. You also are going to have to be able to interpret these types of graphs. So what they did is they plotted all of the different atomic radiuses versus the atomic numbers. If we're looking at, for example, this one, Okay, this little group, this is period 2. It starts with lithium, ends with neon. So what's happening as you look at the atomic radius? Well, it goes down. Okay, it doesn't decrease at an indirect rate. It more is of an inverse type of relationship, but as you notice, it decreases. Okay, so that's where you get that trend. The other one that you want to note is when we look at hydrogen, lithium, sodium, potassium, rubidium, and even though the lines are not connecting, even though the lines are not connected like they were in this part of the graph, what you are changing when you're going from this one is you are going down a family. What that means is you are going down a family is that if you notice, the general trend is that it increases in size. And why? Because you are adding those energy levels. So once again, I want you to really understand the definition of atomic radius, and then also know that your atomic radius, the largest, is Fr or francium.